Okay, thank you so much for the invitation. The title of the paper that I'm going to present today is Monetary Policy and Redistribution, a look under the hedge with tank. Okay, so this is joint work with Chris Nobert, who is PhD student at the Graduate Center. He's only third-year PhD student, so we wrote this paper when he was in his second year. Okay, so this paper will be related to HANC literature. As you know, for decades, monetary policy was done with representative agent models. However, recently, economists became more interested in studying how distributions affect monetary policies and how monetary policy affects heterogeneous agents. So obviously, these kind of questions are not feasible to study within a representative agent framework. So people became more interested in heterogeneous agent new Keynesian models. Okay, and the questions that economists address within this heterogeneous agent new Keynesian model literature as follows. So they look at how responses to monetary policy differ across heterogeneous agents. And then, given these differences in responses, how they affect aggregate responses to monetary policy. Also, so how does heterogeneity affect monetary policy transmission? So what are the channels through which monetary policy transmits in the economy? Next question would be, how does redistribution across different types of people affect individual and aggregate outcomes? The next question would be, how do different types of shocks affect inequality? So this HANC models, they are a good tool for studying distributional implications. And finally, so also very important question, how does heterogeneity affects equilibrium uniqueness and other properties of solutions? So in general, HANC models are very complex models. So they are of crucial Smith because they need to study the evolution of distributions over time, and they study how distributions affect aggregate dynamics. So to solve this model, people use pretty complicated numerical techniques, and in recent years, we've seen a big increase in the offer of different methods. Some examples are, for example, Aachen with co-authors, or Bayer and Lütike with co-authors. So these are not very straightforward, I would say, numerical techniques. So I also worked on numerical methods, and recently we developed a method that exploits artificial intelligence techniques, namely deep learning, and uses software that is available in other fields like Google TensorFlow, which allows us to solve heterogeneous agent models with many agents, like 1,000 agents. And these are models of crucial Smith type, where you have distributions evolving over time. So one problem with this way of studying HANC is that numerical solutions are non-trivial to compute, and actually they are not very conclusive. So once you compute the solution and get a number, it's really hard to interpret why do you have this result. So what would change if you, let's say, modify parameters? So you cannot really trace really good the effect of parameters. And so given this, there is a need for more straightforward and simple models where you can conclusively analyze the effects of heterogeneity on the outcomes. And this is precisely the question of this paper. So we set up a simple two-agent New Keynesian model, which is called TANK. And we try to address the above 5 questions that are studied in Hank literature in the context of this more simple model. Okay, and because we are able to derive analytical results, and because also we managed to derive closed-form solutions, we will be able to trace the effect of different models features on aggregate and individual outcomes. Okay, so before I talk about, so any questions here? So this is kind of a broad question that we want to address in this paper.
Hi, I am Ernesto Pasten. I have a quick clarification question. By addressing this question, are you going also to compare to the full-blown Hank model?
No, because I mean, so first, by 2 reasons. So first, we had already too many things to compare. So you leave 1 question per 1 paper. And the second, so there is some literature. I will mention it when I talk about my literature review. That is already doing this, okay? And so they didn't actually find big differences between TANK and Hank, which is also kind of supportive of our results, because then one can kind of extrapolate and say, okay, everything that we found here for TANK model should be in general true for Hank model. But there is a paper by De Bartoli and Gali that precisely does this. It compares TANK to more general Hank, and they found that there is not much difference in, let's say, responses to shock, aggregate shocks, or other implications.
Sorry for insisting on the point, but I thought that that paper is being, the quantitative prediction of that paper is being overturned after that paper come out. That's one thing. And second, that paper is about the aggregate implications of the models, and not all 5 questions that you have, which some of those are related more to the heterogeneity itself.
I'm not sure about overturned, so maybe we can discuss it later. About the aggregate implications, you're right, so they don't look at any distributive implications. So then another answer that I can give that yes, so there is kind of still room for additional work, so which can be done by us or by someone else in the future.
Thanks.
Thank you. Okay, so before I talk precisely about what we do in this paper, let me just particular type of monetary policies that we are going to focus at in this paper. I will be talking a lot about forward guidance policy, and so I need to define it in some clear way. So as you know, before Great Recession, central banks use Taylor rules. So in the slides, you see stylized Taylor rule depending on inflation gap and output gap. So it determines nominal interest rate, and it also, as a variable, includes exogenously given desired interest rate. So central banks are usually kind of following this types of policy rules in normal times. However, when the interest rates was at 0 lower bound, so the central bank was not able to follow this rule, and therefore we have seen the appearance of new monetary policy tools like forward guidance and quantitative easing. So forward guidance is an unconventional monetary policy rule when instead of stimulating the economy directly with the interest rate through this stylized Taylor rule, the central bank promises that it will change the interest rate in the future, and these future promises have effect on today's economy. And so there is a very strong result in the literature that if you look at the representative agent model, it predicts very large effects of forward guidance regardless of how far in the future the guidance takes place, and this result is referred to in the literature as forward guidance puzzle. So in this paper, we're not going to talk about zero lower bound, but instead we are going to talk about normal times, so that the economy is away from the lower bound. However, we are still going to analyze forward guidance policy. So why? So first, it is known from other historical episodes that forward guidance actually was not invented during or after the Great Recession. It actually was applied before as well. Like you see here, some references on empirical papers that analyzed periods prior to the Great Recession, and they found strong evidence that the central banks did use forward guidance in normal times. Another motivation that we have that given the recent episode of Great Recession with zero lower bound, when the nominal interest rate at zero, in order then to kind of increase interest rate, the central bank needs to provide guidance in its formal statements with respect to removing this guidance as the economy recovers. So you see these red dots is when statements about the changes of future interest rates were made, which can be interpreted as forward guidance. And so it's natural to have forward guidance policy once we want to go away from zero lower bound and set nominal interest rates above zero. Okay. So let me then move again to the paper and specify more clearly what questions we address in this paper. So we will talk about three things: monetary policy, redistribution, and inequality. So when we consider different types of monetary policy, we try to see how redistribution in terms of assets and labor income is interacting with monetary policy, and we will consider the effect of redistribution on transmission of contemporaneous and future shocks. And by future shocks, I mean forward guidance shocks. So we will interpret future shocks as announced one-time shocks. And so we will only focus on the case of normal times. So the economy is not at zero lower bound, and the central bank uses active policy and applies forward guidance. In terms of redistribution, we'll study how taxes and transfers affect the outcomes in the economy. In particular, we'll also talk about properties of solutions and determinacy and determinacy regions. So when this solution that we have in the model is unique. About inequality, we will consider the behavior of consumption and income inequality with changes in demand. So there will be demand shocks or supply. So there will be impacts over the business cycle. So our distinctive feature is that we will use closed form solutions. So we derive closed form solutions for both deterministic and stochastic model. We do it for general policy rules. So we do not focus on simplified policy rules as it was done in many prior papers. And we'll talk about so inequality in the steady state and also over the business cycle. Okay, so let me just briefly mention a few papers that are related to this paper. This slide is actually listing the most classical tank papers. So the first papers were by Gali 2007 and by Bilby 2008. So they incorporated into the otherwise standard New Keynesian model two agents that differ in the ability to save. In particular, so they introduced limited asset market participation on the side of one type of agents. They also incorporate redistribution by introducing taxes and transfers. So the common feature is that between these two papers is that they kind of analyze different monetary policies on aggregate outcomes, taking into account this heterogeneity in the economy. So a more recent paper by Di Bartoli and Gali, as we mentioned, makes a comparison between numerical Hank and Tank. So in Hank, they have incomplete markets, idiosyncratic shocks, aggregate uncertainty, borrowing constraint. And they conclude that a reasonably calibrated tank actually behaves very similar to the model with more agents and with incomplete markets and so on. Okay, so these papers, they are analytically tractable, and this makes them kind of comparable to what we do. Not sure what happens to that slide. I think it tells me that I need to skip the slide. I don't know why I can't see it. Can we see it? I think it's blurry.
No,
it's blurry.
Very blurry.
Yeah, I don't know why. So the first one is good, this one is not, and then the next one is good. Okay, so I don't have any choice. I will skip this. So this slide was about another literature that analyzes analytical tank models. They introduce idiosyncratic uncertainty in tank model. However, they afterwards make very simplifying assumptions to reduce the analysis to very simple system of equations, so they don't need to solve their models numerically. So one example would be this Senk model by Bilby, or Acharya Dogra paper about Hank model with exponential utility. So because of exponential utility, they are able to derive analytic results, and so these simplifying assumptions allow them to obtain tractable model, however, at some cost. Okay, and so finally, I would like to mention some literature on monetary policy transmission. So first of all, the paper by Kaplan. This paper started the analysis of decomposing monetary policy effects into direct and indirect effects. So they found that in a representative agent model, monetary policy works almost exclusively through intertemporal substitution, which they call direct effects. And the responses to induce changes in income as a result of change in interest rate are very small. So this was interpreted to be indirect effects. And then they compare this direct and indirect effects in tank model and in Hank model. For tank model, they, for example, found that the share of responses to changes in income is proportional to the share of non-savers. So I will later comment on more results that they have obtained, but basically they seen that when you incorporate a heterogeneous agent, the role of direct and indirect effect switches around. So indirect effect becomes more important than direct effect in the heterogeneous agent model. Okay, so the broad conclusion is that underlying structure of Hank economy plays a key role in monetary policy transmission. So depending on how you parameterize the model, you can get either one effect important or the other. Okay. Let me just mention a few results of our paper. I will probably skip most of this and just tell you about the structure of our analysis. So first of all, we consider two tank models, tank with no capital and tank with capital, okay? So we will explain why do we need tank with capital. So the idea is to look at the predictions of tank in all those dimensions like distributions, inequality, monetary policy transmissions, and see how well we're doing. And if something is not close to the behavior in the data, we would like to think of some possible extensions. And so we do these extensions with introducing capital. In particular, we do it to correct some of the drawbacks in predictions by tank with respect to inequality. Okay, so only a few results about no capital tank. We consider different types of transfers to constrained and unconstrained people. So some people will be savers, others will be non-savers. And so we will see how real interest rate cards responses will be affected by the systems of transfers that we are going to introduce. Then we will also look at predictions of the model with respect to equilibrium uniqueness depending on our distribution system. And so we'll see how different transfer schemes affect equilibrium determinacy. Then we will also show that indirect effects drive consumption response to future shocks if we have many of constrained people. So for redistributional implications or for distributional predictions of the model, we will look at the following. So we know that in the data, consumption and income inequality are counter-cyclical, with consumption inequality being more counter-cyclical. Okay, it turns out that stochastic no capital tank model predicts that both the cyclicality of consumption inequality and income inequality are determined by markups. Okay, and so no other factors affect this. And so when we introduce capital in the model, we kind of break this one-for-one relationship between markups and inequality. So we kind of think that it's wrong when inequality is just traces one-for-one behavior of markups. Okay. So this is the outline of the presentation. I will first present the model with no capital, and then I will introduce capital to talk about inequality, because this is where the no tank capital model, no capital tank model fails. For the first model, I will consider the following topics. So I will talk about forward guidance policy, individual responses to monetary policy, transmission of monetary policy, and inequality over the business cycle. Okay, so all these things like 1, 2, and 3 are not discussed in the context of the second model. We only look at inequality. Okay, so any questions so far? Okay, so let me then start the model. Okay, so I will talk about 2 types of consumers. We assume that agents can be either constrained or unconstrained, and so they will have superscripts K and U. Constraint is denoted by Q because Keynesian consumers, the difference is that constrained people, they cannot invest and they only can work, while unconstrained agents, they can invest in this model. There are 2 assets, so they can invest either in bonds or in shares, so they can hold shares of the firm. Okay, so the share of constrained agents is denoted by lambda, and lambda is between 0 and 1. So suppose we first consider unconstrained agents problem. He maximizes discounted lifetime utility subject to his budget constraint. So we allow for preference shocks in his momentary utility function. He does value leisure and denotes his labor. Okay. In the budget constraint, we see that this agent can either hold bonds, and the constraint is written in real terms, so everything is divided by prices. Or he can also hold shares denoted by F. Okay. So on the right side, so he gets payment on his previous period bonds holdings. Okay. He gets wage. Let me explain this first term in front after. And then he can sell his shares at the price Q, or in addition, he can get the dividends denoted by D from the ownership of firms. Okay. So again, I will explain now delta. And so the last 2 terms represent the transfers that the government pays to this agent. And there are 2 types of transfers. Those that come in from dividends and the other ones that are coming from labor income. Okay. So the constraint is mostly standard, except of the appearance of these parameters delta and delta W. Okay, so let me explain what is that. So think of these 2 deltas as shares that government collects from illiquid profits or labor income taxes, and then uses these resources for distribution between constrained and unconstrained people. Okay, so if we have, let's say, illiquid profits, then delta multiplied by dt, which are dividends, will be the amount that this government collects from constrained people and destinies for a distribution. And therefore, 1 minus delta is the part that is left for the unconstrained agent for its own consumption. Okay. For so this delta is our choice parameter that kind of affects the degree of redistribution between the agents. Okay, so similarly, WV is our share, in this case, of labor income taxes. Therefore, we will see terms like delta W multiplying the wage of unconstrained agents. So we kind of collect this amount from this unconstrained agent. We'll also collect some part from a constrained agent, and then we sum up the total amount and redistributes across agents. Okay. Any questions here? Yeah.
Ernesto Bastan here. Conceptually, what does it mean illiquid dividends?
Yeah, so I think it's a different sense, because I mean, maybe you are familiar with illiquid assets that are modeled in Kaplan-Violante paper. No, in their paper, illiquid means that they are subject to adjustment costs, so that you can freely convert them into assets that you can use. No? So here, the interpretation of illiquid asset differs. So our illiquid profits are untraded and therefore not held in an account of the unconstrained agent. While so in the case of Kaplan, illiquid profits are distributed to the account which is subject to transaction cost. So in our case, we have a different interpretation of illiquid assets. Okay. So
that's why I'm asking. So when this is still a dividend, or is the total profits?
Say again.
D is the dividend or the total profit of the share per share?
Total profit of the share. I would say it's dividends.
So then I don't get in practice, what does it mean that part of the dividends is not liquid? Because that's paying cash. You see what I mean?
So what, in your opinion, if it was different, what would be the interpretation?
I mean, for me, dividend is just a flow of cash that I get, so it's completely liquid. Something else would be if firms decide that not to distribute in dividends all their profits, some of that gets reinvested within the firm, and that will affect the price Q in some way, but I don't know whether there could be some possible way if the shares are not easy to trade, maybe it won't be reflected completely in Q. I don't know, but the mechanism will be more complicated. But the dividend is a cash that I get from the firm that I own.
So I think the sense in which it is a liquid is that so they are untraded. Okay, so for the kind of held in the account of unconstrained agent. Okay, so basically it's not that they can go and sell it very easily.
Okay. Okay. Thanks. Go. Yeah. Thanks.
Okay, so supply side is very simple. So we have followed the assumption in the Bertolli and Galli that assumes that so the wage is at the level such that all agents want to supply labor, and this implies that so we can simplify and assume that wage is just a constant share of some marginal utility of consumption to marginal utility of labor. And this will also imply that the constrained and unconstrained people, they supply the same amount of labor. So this simplification is actually not crucial. So you can extend the model and allow both constrained and unconstrained people choose labor freely without the restrictions that wage is constant share of this ratio of marginal utilities. So what will change in that other model is that some aggregated conditions will depend on additional heterogeneity parameters. And although everything numerically stays the same, but it will be harder for us to prove analytically the interaction between the heterogeneity parameters and redistribution parameters. So we decided to stick to this more simple model in order to preserve analytical tractability, but all the results that we checked hold without any modifications if we just allow our constraint agent to maximize his utility and choose labor freely. And so there will be differentiated labor in that case. Okay, so then we assume that firms use only labor and they are subject to productivity shock, which follows first order after regressive process. We assume Rothenberg pricing, which leads to the standard Phillips curve. And for future, so this mu with superscript P denotes average gross markups. So this will play key role when we talk about our distributive implications of the model. Okay, so let me describe our redistribution rules. So we have the distribution of profits and wages or labor income taxes. Okay, for profits, we say that the total amount that was collected by the government for the purpose of redistribution is split between constrained and unconstrained agent in such a way that constrained agent gets 1 minus tau or share of total resources available. So basically when tau is equal to 1, if tau is equal to 1, then this lump sum tax that constraint agent gets is equal to 0. So constraint agent does not get any profit redistributed, so no redistribution. So similarly, for labor income tax, since both constrained and unconstrained agents get labor income, so by then redistributed in some way, we can either favor unconstrained or constrained agents. So formula for, let's say, constrained agent will be similar. So you multiply total amount available for the redistribution by the share 1 minus tau v or tau w. However, this tau w is not in 0 and 1, as it was in the case of liquid profits, but it is allowed to be negative. Okay, so if, for example, this tau w is equal to minus 1 over lambda, if you substitute it into this formula, for example, you will get that with this share tau w, unconstrained agent does not get any lump sum transfers of labor income taxes. Okay, so then the case when there is no redistribution will be for tau w equal to 0, because tau w equal to 0 will imply that each of the agents will just get lump sum transfers equal to what they pay as taxes. Okay, any questions here about this two redistributive or transfer schemes? So what we are going to see is that these two, they will kind of play different roles in many places like transmission or the effect on heterogeneity and so on. So they will mostly work in opposite directions. So given this redistributive schemes, we will refer to parameters tau, w, delta, delta, w as redistribution parameters. So they will be choices by the government, and so by varying their values, we will be able to see how redistribution affects the outcomes in the economy. So as I mentioned, the idea of our analysis is to obtain closed form solutions for the model. For this, we need to linearize or log linearize the model and simplify it in such a way so we have the least possible number of equations. So first, there are very simple ways of representing the relationship between aggregate and individual variables in log linearized model. So suppose this productivity shock in log terms is equal to 0, then there will be simple formulas that relate aggregate consumption and individual consumption. So the key parameter in all our analysis will be composite parameter phi. Okay, I did not provide the formula here, but I will just let you know that it depends on all our heterogeneity parameters, which include lambda, which is the share of constrained agents, and the other parameters related to distribution, as well as other models parameters, okay? Like utility function parameters, and so on. And so this composite parameter will determine like the effect of heterogeneity on models' aggregate behavior. In particular, one can show that the Phillips curve in this heterogeneous agent model will be the same as in standard representative agent model. However, Euler equation will differ, and this difference will lie only in this one additional term, which is 1 minus phi. So basically, we can summarize all the heterogeneity by this composite parameter phi. And we can see how to set this phi so that we go from heterogeneous agent model to representative agent model. In particular, there are two possible ways to go from heterogeneous agents to representative agent setup. So clearly, if you assume that the share of constrained agents is 0, lambda is equal to 0, it will lead to the economy in which all people can invest and save, the standard representative agent model, so that it will imply that phi is equal to 0. However, there is another case when phi is equal to 0 as well. So this is when we set tau equal to 0 and delta equal to 1. So if we go back to our redistributional schemes, so when you say tau is equal to 0 and delta is equal to 1. Okay. So when tau is equal to 0, then tau k is equal to delta dt, okay? Okay, and everyone therefore gets the same amount of profits, okay, or dividends. So therefore, given that everyone also supplies the same amount of assets, and given that they will get the same amounts coming from profit. So each agent in the economy will be the same. So there will be representative agent. Okay, so let me then also talk about our closed form solutions. So first, I should emphasize that all our results are obtained for generalized Taylor rule. So by generalized Taylor rule, I mean a rule that includes not only either inflation gap or output gap, but also expected inflation. And this included one by one, but all three possible terms like YT, expected by T plus 1, and YT are parts of this Taylor rule. So we are kind of emphasizing that it is important not to reduce this Taylor rule by just focusing on one of the variables, because any kind of reduced Taylor rule leads to simplified results, and so the results are not sufficiently general. So previous analytical tank literature, they either considered rules in which there was only one phi parameter which is not equal to 0, so they only include like one variable affecting nominal interest rate. And moreover, they focused on some particular parameterizations of Taylor rule. So one popular rule was introduced by Bilby, or not introduced, used by Bilby, McKay, Nakamura, and Steinson. We refer to this rule as reduced Taylor rule. So in this case, it includes expected inflation on the right side of the rule, but also the coefficient is equal to 1. So this phi of E pi is equal to 1. So this rule was shown to be useful if one wants to analyze effects at a zero lower bound. I have some figures in the future to illustrate why this is the case. But anyway, so because of the simplification, many of the results, so they are not quite general. So we will show that we have different implications just by extending this rule. Okay. Okay, so let me describe our second order difference equation. So it turns out that you can represent all the equations in this tank model by just one equation. And this one equation is in terms of inflation, so you don't have any other variables. It is a second order difference equation. So it is a summary of all equations like Taylor rule, aggregate Taylor equation, and Phillips curve. In this second order difference equation, B and C are constants. Okay, so you see the definitions here. They depend on, let's say, heterogeneity parameters, and also Taylor rule coefficients and other parameters of the model. And there is another variable xt that also depends on heterogeneity, like phi parameter. It includes all sources of uncertainty in our model. For example, I have forgot to mention that in Taylor rule, my monetary policy shock, VT is following first order autoregressive process. My desired interest rate can also follow some process, or it can be given just by exogenous path. Other exogenous shocks would be a preference shock that we have seen before, or productivity shock. So all of these exogenous variables are summarized in this variable xt, which is very convenient. So we don't really need to kind of study interactions between these shocks and are able to just look at xt value. Okay. So given that we can summarize those equations in the form of one second order difference equation, we will be able to derive explicit solutions. And by solutions, I mean not only what is usually done in the literature, so find general solutions. So we actually are going to extend this result and provide general solution plus particular solution. So particular solutions are obtained for some specifications of shocks, and they are not very commonly used in the literature because, I mean, it's not trivial to derive them. So I had another paper with John Taylor in which we derived this closed form solutions for representative agent model, okay, and so extend those results here for Hank model. Okay, so to derive these closed form solutions, we assume that somewhere in infinity the economy becomes stable. Okay, so it converges to the steady state and transversality condition is satisfied. And so we derive those closed form solutions for 4 different cases, depending on the values of eigenvalues of the second order difference equation. In particular, eigenvalues can be distinct or the same and repeated. So we can have real roots or complex roots. And within the class of real roots, depending on the values of eigenvalues, we can have either indeterminate solution and unique solution. So let me just, for simplicity, skip the cases of complex roots and repeated roots and consider real roots. M1 is not equal to M2. M is eigenvalues, such that they are either bigger than 0. Both of them bigger than 0. This is a case of unique solution, or one is bigger than 0 and the other is smaller than 0. So let me just briefly show how these closed form solutions work. So for general solution, we have standard summation, which is m to the power of t, weighted by constant of integration, C1 or C2. And in particular solution, we have summations, okay, these 2 sums that you see, for example, in this formula. They are constructed in such a way that depending on if M1, for example, is bigger than 1, and S goes to infinity when we substitute these values into the sum, so the sum goes to 0, so that we do not explode and convert to the steady state. Okay, so this is a very simple idea. So, but anyway, so because so this kind of new kind of solutions that were provided first by Maliar and Taylor, and so we use them here, but we found them as useful for tank model as they were for rank. Okay. Okay, so given the solutions, we are able to derive many analytic results. Okay, in particular, as I mentioned, we are going to work with general Taylor rules that includes all these determinants of nominal interest rate. And we will characterize the properties of the solutions depending on the Taylor rule coefficients, like phi pi, phi pi, phi y. Okay. And so one thing to observe that there will be bounds on types of solutions. And the 2 bounds that determine whether solution is unique or indeterminate will be phi e pi 1 and phi pi 4. So as you may see, in the first one, there is no phi, which is my heterogeneity parameter. And in the second case, we do have phi, okay? So that means that my heterogeneity will have effects on the areas of indeterminate solutions. So depending on how we specify our redistributive parameters, we might have distinct indeterminacy areas, okay, in heterogeneous agent model compared to representative agent model. So this can be seen, for example, on this figure. So here we draw for different values of lambda, rank model corresponds to lambda equal to 0. Then we have two other values, 0.21 and 0.38. 38 means that 38% of agents are constrained. Okay, and so you see that so the areas that separate different kinds of solutions differ across models in which we specify differently lambda. Okay, so let me explain the colors. So in white we have complex roots, so these are unique solution, but roots are complex. In gray we have real roots with unique solutions. In black we have indeterminacy. So if we are concerned with indeterminacy, so the biggest areas of indeterminacy are obtained for larger lambda when we have very many unconstrained constrained agents. So there are big restrictions to asset market participation. And we can see that actually, so for some parameterizations, this values in terms of phi pi, so on this axis you have phi pi, could be kind of empirically relevant. So, for example, this point that I'm showing now corresponds to the Taylor rule when phi pi is equal to, let's say, 3, or maybe 4, let's say 4, just here. So then it will lead to indeterminate solution. So phi y is equal to 0 in this case.
Lilia, you have around 25 minutes.
Okay, thank you. I think I'm not going well on time.
All right.
Okay, so, yeah. So let me just mention here that in the paper we derived analytical result that show how my composite parameter phi depends on the redistribution parameters. Okay, and so for example, we've seen that this lambda will positively affect phi. So the larger is lambda, the bigger is phi. Okay, and so the larger is phi, the smaller is this upper bound on indeterminacy. Okay, and therefore we see this positive dependence of black areas on the value of lambda. Okay. So in the paper, we explain why in some cases, for example, point like this, we do have indeterminacy for Hank model, but in rank model, it would imply just a unique solution. So we have some intuition behind this, and we explain that it is related to the fact that in tank, we have amplified effect on labor supply of heterogeneity. Okay, so then we also analyze how my other heterogeneity parameters, like let's say tau and tau w, affect these composite parameters. And composite parameter is actually related to elasticity of substitution. Okay, like intratemporal elasticity of substitution, given that it appears in my Euler equation together. So everywhere where I have sigma, which is a utility function parameter, I will also have 1 minus phi in heterogeneous agent model. So in this case, in heterogeneous agent model, sigma 1 minus phi can be interpreted as sigma in the representative agent model. So this kind of allows us to nicely interpret the effect of this composite parameter phi. Okay, so what we can see from these colorful figures that my redistribution parameter affect differently this 1 minus phi. So I think on this side I see 1 minus phi, and this side I have this upper bound on in the terminacy area. So in particular, for example, when we write tau and tau w, so the lambda, okay, so here I have lambda. The lambda depends on tau for fixed value of parameters 1 minus phi or phi by 4 will behave differently. In particular, we see that the slope of the lines in these figures 2 and figures 3 are different, so meaning that so my composite parameter is more sensitive to tau than tau b. So we can achieve more if we want to get different predictions in heterogeneous agent model by varying tau than tau v. So tau b is kind of less relevant. Okay, so let me then switch to forward guidance. So let me say first that because of closed form solutions, we can analyze this forward guidance policy very easily. So why so? So think of forward guidance is one-time anticipated shock. Okay, so suppose at t equal to 0, the central bank announces that at t equal to 30, it will change the interest rate, okay? And so there will be some anticipatory effects by the agent. So if you solve the model by normal tools, you actually cannot incorporate nicely these anticipatory effects because the model will be actually non-stationary. And so you need to use tools that allow you to solve non-stationary models, okay? But with closed form solutions, you have explicit formulas that tell you how your variables will react to this one-time anticipated shock. Okay, so these are examples of such formulas. So you can obtain explicit formulas for all the model's variables given closed form solutions. And so what we have done then to analyze forward guidance policy depending on parameterization of the Taylor rule. So one case is when we set phi pi equal to 1 and all the other coefficients are equal to 0. So this will correspond to the Taylor rule in which you have only expected future inflation, and so the coefficient in front is equal to 1. So as you might know, in the previous literature, this Taylor rule was used to model zero lower bound because it leads to a constant real rate up to the period of the shock. So here the shock happens at t equal to 30. And so if you analyze the impact of this anticipated forward guidance shock at t equal to 30, you will see that there is immediate effect on output, which is larger when we have more constrained agents. So if lambda is 0.38, so the impact on output is 16%, which is much larger than for the case of lambda equal to 0.21, meaning that heterogeneity amplifies the effect of forward guidance on the economy. So the same is true for inflation and nominal rate. Okay. And so we do see forward guidance puzzle in the heterogeneous agent model if we assume this reduced Taylor rule. Okay. However, if we consider the standard Taylor rule parameterized by phi pi equal to 1.5 standard value and phi y, which is greater than 0, so we'll see that forward guidance actually has reasonable effects. It does not lead to jumps in all the model variables upon the announcement at equal to 0. So the shock only affects the economy when we approach closer to the date of the shock, t equal to 30. Then yellow line, which is lambda equal to 0.38, shows that the effects at the peak are larger when we have many constrained agents, meaning that so the monetary policy effects are amplified with heterogeneity. However, so the dynamics is not like in the previous case, so we don't have really forward guidance puzzle for the case of the standard Taylor rule. Okay. And so what is curious, and this figure shows this, that even small parameter phi y, like 1%, would actually break the forward guidance puzzle. So you see that if we, in the previous first figure, add this additional parameterization for phi y, actually we don't have any forward guidance puzzle anymore at t equal to 0. So the output for lambda equal, let's say, 0.38 behaves reasonably. There is no anticipatory effects at t equal to 0, and only observe some bigger effects at the peak or in the period when the shock happens. So we derive the formula for consumption that explicitly shows discounting of future shocks, and discounting of future shocks depends on our composite parameter phi. Okay, so I have 70 minutes almost. So let me talk about individual responses to monetary policy shocks. Okay, so because of closed-door solutions, we are able to derive explicit formulas for consumption of two types of agents. And as you see, they do not depend only on the shock, but also on some parameters as h, which includes the following determinants. So it depends first on the time of the shock. So how each consumer responds to one-time future shock will depend on the shock horizon t. It will depend on all coefficients of the Taylor rule, and we provide a formula that explicitly shows this dependence. And it also depends on the eigenvalues. So depending on how big is the difference between two eigenvalues, you will obtain different effects of shock on individual consumption. Okay. So if you have a reduced Taylor rule, the standard rule that is used to analyze effective lower bound, and set phi pi equal to 1, it turns out that this variable h becomes 0, and then you can easily see how each agent responds to shock. In particular, unconstrained agent just directly responds to monetary policy shock, so there is no dependence any longer on time horizon of the shock or parameters of the Taylor rule and so on. So this is for unconstrained agent. So for constrained agent, again, no dependency on horizon t. So one thing that I would like to point out that this parameter x, which is bigger than 1, tells us about amplification of monetary policy. So if there is a shock, okay, because x is greater than 1, so consumption of constrained agent will respond sufficiently strongly, and will have overreaction by constrained agent relative to unconstrained agent. So this could be seen, for example, on these figures. On the left side, you have the rule which corresponds to reduced Taylor rule, and the right panel represents the standard Taylor rule. So as I have mentioned, for reduced Taylor rule, constrained agent, he has this red line, okay? He kind of overreacts, and he responds to the shock by increasing his consumption by 5%, okay? So the figure plots consumption responses depending on the horizon of the shock. So on the horizontal axis, we represent T, okay? And for this reduced Taylor rule, we see that response of any of the agents depends on shock. So these are horizontal lines. And again, constraint agent like reacts excessively. So the same is true for the standard Taylor rule. So you see that the red line, when we have an increase in consumption, red line increases more than blue line, which is unconstrained agent. However, at some horizons, for example, here when T is equal to 8, the constrained agent actually reduces his consumption, and this reduction in consumption is more significant than for unconstrained agents. Okay. Any questions so far? Okay, so let me then move to, I think, most novel part of our analysis, which is transmission of monetary policy. In particular, starting from paper by Kaplan, Moll, and Violante, people look at the composition of monetary policy effects into direct and indirect effect. So, let me mention that direct effect captures the response of consumption when the real interest rate changes. Okay, so this in terms of real interest rate, we have this term IT minus expected by T. So this is a real interest rate. And so I repeat, direct effect capture the response of consumption when the real interest rate changes, keeping income fixed. And indirect responses reflect the change in consumption due to change in income or output gap, keeping the interest rate fixed. Okay, so you can derive a simple log linearized formula for planned expenditure curve, which allows you to split the total effect on consumption when there is a monetary policy shock into this direct and indirect effect. So these three parameters, as you might see, depend on your model's parameters as well as your composite parameter phi, which determines the difference between rank and tank. Okay. In these formulas, index J, which you see in these constants, tells us how many periods in the future the rate cut takes place. So, for example, if J is equal to 5, then the interest rate cut happens at T equal to 5, but it is still announced at T equal to 0. Okay, and so for different types of solutions, this other parameter rho J, which is like a kind of persistence of consumption over time. So it relates CT plus 1 and CT. So it will be different depending on whether we have complex root or indeterminacy and so on. And so we derive this analytically. So this helps us to better quantify the direct and indirect effects. And then we analyze the decomposition depending on whether we have transitory shock or permanent shock, and whether we have future shock or contemporaneous shock. Okay, so we'll consider also different kinds of solutions. Okay, so okay, so basically when J is equal to 0, it means that we consider a contemporaneous shock. Okay, but we also consider J equal to 1 and J equal to 5. So suppose the shock is produced at J equal to 5, it means that this is forward guidance shock, which is announced at T, it happens at T equal to 5, and it's only one-time shock. Okay. So what do we see here? So first, we see that for, let's say, for different models, independently of the value of lambda, so we consider for tank value 0.21 and 0.08, and for rank we have lambda equal to 0. So first thing to observe that so by looking at here, we see that direct effects for contemporaneous shocks work in direct and indirect effects for contemporaneous shocks work in the direction of an increase of consumption. So basically, both of them are positive. Okay. And then, if we look, for example, here, okay, so we see that so the direct and indirect effect work in opposite direction, okay, in both rank and tank. So this is for tank and this is for rank. Okay. And then if you look at low lambdas, so if I focus at, let's say, cases like this for low lambdas, then we see that indirect effects of future shocks work to reduce consumption. Okay, so both in both cases we have a negative sign for indirect effects. And then what else I can say here? And so like if we look at this one, then we see that indirect effect works to increase consumption. Okay. And this is different from when lambda is equal to 0.21. So basically when we have sufficiently many constrained agents, indirect effect works to increase consumption, as opposed to the previous case, numbers like this, when we have small lambda, then indirect effects works to decrease consumption. Okay, so then we also consider, let me move on, consider direct and indirect effects for the case of indeterminate solution. Okay, so here the findings in some cases are similar, in some cases are different, so I will not focus on that. So in addition, we considered the case of persistent shocks, and this could be as a contemporaneous shock or future shock. So by persistent shock, I mean that it happens today and then it follows first order autoregressive process formula without new shocks. And so for this case, the tendencies are very similar to non-persistent shocks, but we found very unusual results that aggregate marginal propensity to consume is negative, and we give intuition behind this result in the paper. Okay, so I have only 7 minutes to talk about inequality. So let me mention that closed form solution allows us to derive explicit formulas for stochastic model, and this allows us to analyze volatility of individual consumption depending on the shock in the economy and depending on redistribution heterogeneity parameters. So formulas with closed form solutions look like this, for example, for inflation. And they are convenient because so we can just plug them in to compute volatilities of consumption of individuals and like explicitly characterize and prove propositions on what happens in different economies with different redistribution schemes. In particular, proposition 2 for one specific case of solutions found or verifies that if we have 2 economies such that for one economy, phi1 is greater than phi2. So these are composite parameters. They don't have any interpretation. So for two economies, they happen to be different. Then it will be the case that the standard deviation of output gap for economy with larger phi will be larger. So there will be more volatility in output gap depending on larger value of phi. Okay, so in words, output gap volatility is higher in economy with larger tau. So larger tau implies larger phi, and therefore the economy with less profit redistribution will have a higher volatility of output gap. Okay. So we investigate the effects of phi and redistribution schemes on volatility of consumption of different types. And we found actually that if you go from the benchmark case when there is no redistribution, tau equal to 1 and tau equal to 0, to the case with redistribution such that so the corresponding taus are not as in the case of no redistribution, you can actually obtain the result that with redistribution of illiquid profits, consumption of two types of agent can fluctuate less. Okay, so by redistributing illiquid profits from unconstrained to constrained, you can achieve lower volatility of consumption of both type of agents. And this is because even though when you redistribute, you take away resources from unconstrained people, you still have effect on aggregate demand. So aggregate demand is less volatile, so they kind of gain in that direction, so that the total volatility of consumption goes down. Okay, so inequality in this model is not interesting to study because as we show, it maps one-to-one the behavior of markup. Okay, so there is this result, which is actual standard in this literature. It was shown by Bilby, that consumption inequality gap is a constant multiplied by markup. Okay, so if markup is going up, okay, so it is per-cyclical, then inequality will be per-cyclical as well. If markup is counter-cyclical, then inequality will be counter-cyclical as well. However, in the data, we know that consumption inequality is counter-cyclical, and it's more counter-cyclical than income inequality. Okay, so basically, this model does predict counter-cyclical consumption inequality and income inequality, but at the cost that it produces counter-cyclical markup, which is counterintuitive. So you cannot have counter-cyclical markups. And so in the model with tank, we try to correct this model implication. So we add to the agent budget constraint capital. So now unconstrained agent holds also capital, and we redistribute not only dividends and labor income taxes, but also capital earnings. Okay, and so maybe it's better to see here. So we have only capital added here to the redistribution scheme. Okay, and the rest of the model is the same. So the model also features adjustment cost. We tried different adjustment cost functions and found that it's not kind of important for inequality implications. So we kind of think that the specification of adjustment cost function will not kind of help us to get the inequality right in this respect. So what is different in a model with capital is that now consumption gap is not just markups, but also it will depend on the value of installed capital and interest rate on capital. And given that this Q and RK affect gamma in opposite direction, we can kind of obtain the result that the consumption gap does not follow exactly the markup. Okay. However, income gap is still related to markup directly. Okay. And so in the paper, we talk about inequality responses to demand shocks and to supply shocks and over business cycles. So for demand shocks, we found that consumption inequality, because it depends now on 3 factors, is countercyclical, and it is more countercyclical than income inequality. So this is a positive implication. However, the bad thing that income inequality is still tracing markup, so it's not very satisfactory. For supply shocks over the business cycle, we find that depending on how you specify adjustment cost, consumption inequality can be either pro-cyclical, cyclical, or counter-cyclical. However, the income inequality is highly pro-cyclical. So you can see also in this other table where we vary redistribution schemes. Okay, so therefore we conclude that even though you can break this one-to-one relationship between markups and inequality in the model with capital, you can still have negative features like pro-cyclical income inequality, and so you don't get this tendency or stylized fact, right, with the given model. So one way to deal with it is to introduce the rigidity in wages, okay, and so this will be kind of generating then counter-cyclical income inequality in this model. Okay, so in conclusion, I just wanted to say that the model that we study is simple. It allows for analytical solutions that simplify the analysis of models' predictions in many dimensions. And we think it provides useful insights into mechanism at work in quantitative Banco models. So sorry, I was a bit over, and I think I stop now.
Thank you, Lilia. We are a little bit overdue, so those who want to stay with us after the seminar is over, you're more than welcome to talk to Lilia for some minutes. And the rest of the attendants, thank you so much for coming.